what we got here is two cyclic groups, G1 and G2, each one with its own product, whatever, right? And the order of these two groups is N1 and N2 respectively, right? Let's assume that you have two generators. If they are cyclic, they have to be generated by at least one element, right? So let's say that A1 and A2 are respectively generators of the first and the second group, right? And they are arbitrary. I mean, they can be any generator. So we can assume that A1 and A2 are arbitrary generators of these two groups. So whatever we're going to conclude from this is valid for any pair of generators that you take, right? Okay, now we make the Cartesian product of these two sets, and we introduce the standard multiplication in this Cartesian product. We take this multiplication of two ordered pairs is going to be the multiplication component wise, right? So you have the multiplication of the first components and the multiplication of the second components, each one with its own product, okay? Fine. Now we have to determine what is the order of this element, which is, remember, these are the two generators. So we take the order pair with the two generators, and we have to find what the order of this element is, right? And finally, we have to figure out what is the relation between N1 and 2 so that this group here is a cyclic group, right? Okay, so first question first. So we have this. We have what is the order of this? So the order of this, what we have to do is to take this pair and raise it to the power k, which means, I mean, the multiplication is component wise, so this means that this is A1k, A2k, okay? And we want this to be the identity here and the identity here. This is the identity of the first group, okay, G1, and this is the identity of the second group, G2, right? Okay, so because of this, because A1 to the k is equal to E1, then k must be a multiple of N1, the order of the group, right? So let's say, let's put it in a different way. N1 divides k, all right? Remember, N1 is the order of the group and is the order of any generator, in particular this one. So if this is equal to the identity, this must be a multiple of N1, right? And similarly for this, if A2 to the k is equal to A to E2, then it's because N2 must be a divisor of k, right? Must divide k. Okay, so k has to be a simultaneous multiple of N1 and N2. And not only that, it has to be the smallest possible number with this property. So the smallest possible multiple of N1 and N2. That would be the order, right? And that is, of course, the least common multiple of N1 and N2, right? So that's the answer to the first question. The order of this element, ord of A1, A2, is the least common multiple of N1 and N2. All right, now the second question. Well, it's clear that if we have to generate the whole group, well, we have to put here are generators of G1 and G2, right? Because if they don't generate the group, let's say if this doesn't generate the group G1, then we can hardly generate the group G1 times G2 by using this generator here, right? So A1 and A2 must be generators respectively of G1 and G2. So whatever generator this group has, if there is any, it must be of this form, right? Okay, but we know that the order of this element is equal to this, and the size of this group is equal to N1 times N2. Okay, that is the order of this group. So the condition for this to be a cyclic group is that this number and this number are the same. So this and this must be the same. And remember, this the least common multiple is just N1 and 2 divided by the greatest common divisor of these two. So the condition then is N1 and 2 is equal to 1. So N1 and N2 must be co-prime if this has to be a cyclic group. Otherwise, it's impossible that this is a cyclic group, because the order of the group, the order of any generator, any candidate to generator of this group is smaller than the order of the group, and then it's impossible that it generates the whole group. So it only generates a subgroup, right? So the condition we're looking for is this one. If the two subgroups have co-prime orders, then the Cartesian product can be a cyclic group. Otherwise, it can't.